So in 5.1, we were just graphing functions based on certain information, right? We were checking for asymptotes, we were checking for holes, we were checking for increasing, decreasing, we were kind of just taking a lot of information and trying to create a graph out of it. What we're going to do in 5.2 is now we're going to either graph the derivative function, the second derivative function, or the graph from one of those. The hard part about this section is, what am I looking at? Am I looking at a graph of the function? Am I looking at a graph of the first derivative? Am I looking at the graph of the second derivative? And then going the other direction. That's why it says antiderivatives. So sometimes they'll give you the graph of the first derivative, and then you're going to go backwards and graph the function. And so it's really, really important to understand what it is you're staring at first and what your goal is and where you're trying to go. And as we work through this today, I'm going to talk about a lot of different strategies. Okay, so first off, I'm going to give you a bunch of steps. I don't think these are in the book, and if they are, I retyped them and reworded them. So I definitely would encourage you to write them, okay? So here's what we're going to do to sketch the derivative graph. So let's say you're given the function, and you're going to sketch the first derivative graph of that function. That's where we're going to start here, okay? Now, in order to do that, we got to follow a bunch of different steps, and we're going to look for some very specific areas that we want to focus on to help us draw this graph, okay? So the first thing you want to do when you're doing this, if you're given the graph and you're going to come up with the derivative graph, you want to mark any zeros of turning points or stationary inflection points. Mark zeros at the locations of any turning points or stationary inflection points. And I'll talk more about what that means here in a second. All right, the second we're going to do is, this is something you're going to kind of have to keep in mind. You're going to draw the derivative graph above the x-axis where y is positive whenever the function is increasing, meaning it has positive slope. Therefore, the graph will be in the quote-unquote positive region, and that is where the y's are positive. So we're going to need to know, when we look at the function, where is it increasing? And wherever it's increasing, we know that the graph of the derivative function will be positive, meaning it will be above the x-axis. Okay, so you can probably guess what the next line is going to say. Would you like to try? Below and negative, sure. Okay. So if the function is decreasing, meaning it has negative slope, those numbers will be where y is negative, below the x-axis. One of the things that's really tricky about these kinds of problems is you're holding a lot of things sort of in the back of your mind going, okay, if this, then this. And you have to pay attention to all that before you try to start graphing it and start getting ideas. And as we go through some examples here, I'm going to talk through that, how I would do that. Hopefully that you'll find that helpful. Okay? And then the last thing, you're going to find or estimate slopes on the graph. So in some cases, you're going to be able to actually find the slopes from the function. In other cases, you're going to do kind of a rough estimate, and that's good enough. The one thing I want you to know about problems like this is nobody expects perfection. A lot of these kinds of questions you'll see in multiple choice where they say, here's the function. Which of these are possible derivative graphs? Or which of these graphs could not be the derivative graph? Oftentimes you'll see questions like that. The other thing you'll see is like, here's the function, here's the first derivative, here's the second derivative, and they'll give you those graphs, and they'll say which of these make sense, okay? So kind of keep that in mind. All right, now this is in your book, and if you want to take a screenshot from your book, you can. This is the very first example. I don't have the page off the top of my head. Yeah, so this is page 105. page, oops, 105. And if you just stay in that area, because we're going to use some other examples there, okay? Now, I'm going to go through this one with you and talk about how I would approach this, okay? And I encourage you, if you have questions as we move through it, to let me know. One thing I want to point out, so they're giving us the function. Here's the function f. We're going to draw the derivative graph. In other words, just so we're clear, what we're going to do is we're going to take this graph and find all the slopes, and we're going to make a graph of the slopes. Okay? One thing that I encourage you to think about before you even start, okay, is to try to sort of get an idea of what type of graph this could be in terms of degree, okay? So when you look at this graph, I know you might look at it and it looks like a trig function, but think about degree. What degree could this function be? Could it be a linear function? No, so it's not one. Could it be a quadratic? What's a quadratic look like? Yeah, a parabola, right? Could this be a cubic function, degree 3? Okay, so if we think of cubics, a lot of time we think of things like this. So it's got two sort of curvy parts. Now, if you notice here, they're endpoints. They don't keep going. Could this be a cubic? It could be, okay? Now, it doesn't mean it is, okay, but it could be. So when I take the derivative of something to the third power, what do I end up with? What happens to the degree of a function when you take the derivative? It goes down by 1. So here's why I'm talking about this. Since I know that I'm trying to graph the derivative function of this, and we're saying this could be a cubic, what could this look like? If a parabola, right? If this is degree 3 as a cubic, then the derivative should be degree 2. Now, we don't know if this is a cubic, okay? And we don't know what this is going to look like yet. But this sort of gives you a starting point to be thinking about, all right, does my answer make sense? All right, so here's where we're going to start here. So as I mentioned in the notes, we want to find easy slopes, horizontal tangents, vertical tangents, wherever, okay, if they exist. All right, so right off the bat, start here with 2 horizontal tangents. Okay, what is true about the slopes at the horizontal tangents? What is the slope? What is the slope of a horizontal line? 0. So what that tells me right away, what that tells me is that when x is negative 2 and x is 2, the slope is 0. So I can plot those. Remember, this is a graph of the slopes of this function. So when x is negative 2, the slope is 0. When x is 2, the slope is 0. That's where I'm going to start. Do I have any other super easy ones to find? Okay. Here, the slope of this. Let's do positive ones first. I don't disagree with you, but I didn't put them in that order. We'll get back to that one in a second. But you're right. We should look at the slope for this one for sure. All right. What is the slope of this, by the way? Negative 1. Is there any place that looks like there's a slope of 1? Like, give me an about area for x where slope is like negative 3. So right here we think we have one. Where else? Okay, so then positive 3. Okay, I would agree with that. So here I have a slope of, again, we're guesstimating. We're not going to be perfect here. But what that tells us is approximately at -3, I have a slope of 1, and at +3, I have a slope of 1. Okay? And so it just follows that, of course, if it's positive, if I have positive slope, I have to be above the x-axis because that's where y is positive. All right, now, Adam, let's go to yours. You were talking about this one. This one has negative slope. Okay, -1. So when x is 0, the slope is -1. So what I would be graphing is a point down here. Okay, does this seem like I have enough information?
Yeah.
Seems like it. Now, let's think about our hypothesis at the beginning. We said, hey, this is probably a cubic. Does this look like a quadratic? Yeah, it does. Okay. Now, this could also be something to the 5th power, and this could be something to the 4th power. But if it was something to the 3rd power, and then we would have this 2 turns. We don't have that. Now, there's one other thing we have to be careful of.
So wait, if it was like a sine graph,
Mm-hmm.
like the derivative would be cosine graph.
Mm-hmm.
All right.
We're not going to usually know that, though. They're just going to give us a graph, and they're not going to give us any more context than that. I mean, in reality, this could be a sine graph shifted, and so this could be a cosine graph.
Plug in a number from the graph that you're given, right, and then figure out what graph it is, or have a better idea.
You could. What I would tell you that is that's not the point of that, though.
Yeah.
Okay, we don't want to be perfect here. We want to use these trends and understanding the idea between what is happening between the function and the first derivative and the first derivative and the second derivative and that kind of thing. We'll get into the second derivative here in a second. The one thing we have to be careful of here are the endpoints. Okay, we do not draw a parabola with arrows going on forever. Okay, this graph stops at -3.5 and stops at 3.5. So when I go to connect these, I'm going to stop right there and I'm going to stop right here. Okay. And so that's what my graph looks like. And notice I did put endpoints here. Now, there are always sort of variations that you could have, but if you pick some pretty simple areas to find slope, we're all going to be in fairly strong agreement. Okay? Questions on that? All right, let's change it up. So this is probably on page 6. Okay, now what's going to happen, and this is where it gets a little tougher. Okay, they're going to give you the derivative graph, and we're going to make the function out of it. Okay. So that's why you talk about antiderivatives, because we're going to have to go the other way. So the information we talked about regarding degree, now instead of it going down by 1, it's going to go up by 1. So what the shape of the first derivative graph is going to tell us, it's going to give us information about what the function itself is going to look like. So the first thing we've got to do is you're going to have to make a number line for the first derivative. And you're going to have to use the location or position of the points on that graph. Okay, we're not finding slopes. Remember, the first derivative graph is telling us the slope. So when we look at those graphs and we look at those y values, it's specifically telling us the slope at a given x. And then we're going to use that to help us graph our graph. Okay. The second step after that is we're going to have to make a second derivative number line. Because one of the things that we don't know about our function by just looking at the first derivative is concavity. And so we're going to have to make a second derivative number line. And now we are going to use the slopes from the first derivative graph because we're going to do the same thing. Where is it 0? Where is it undefined? That kind of thing. Because those are potential points of inflection. Not necessarily points of inflection, but potential points of inflection because there has to be that sign change. And that's what this is going to tell us when we do this. We're going to find out if at that particular x value, does the concavity change? And that's going to help us get an idea about the shape of the original function. And then the last thing that we have to do is we're going to take all that information, we're going to take a starting point if it's given, and then we're going to graph it. Now, the thing that you have to keep in mind as you're checking answers and that kind of thing is your function graph for the function f could be different than your friend's or from the answer key if it's a vertical shift. Okay? So it will have the same shape, it should have the same shape. It just might be in a different position. And that's all based on if they've given us a starting point. If they don't give us a starting point, or if they don't give us a point that's included on the graph, it's entirely possible that you could have a different answer from the person next to you. And that they would both be correct. But they should also both have the same shape, even though they might be in a different position. Okay, does that make sense? All right, let's put it all together and try to do one. So this is example 2, still on page 106. Okay. So in here, in this case, they gave us the first derivative. They've already provided us a quote-unquote number line for the first derivative and the second derivative. And then they've given us space to draw the actual function. Okay? And we'll do this one together too. Now what's interesting, this is the exact same graph that we did for the function f in the first example. But now they're saying this is the first derivative, not the function. Okay? So let's think about that. We already said this is probably a cubic. So if I go from the first derivative to the function itself, what would the degree be of this if this was a cubic? This would be fourth degree. If we said this is third degree and we're going from the derivative to the function, then this would be fourth degree. Now, I don't know that you know what a fourth degree function looks like, but I'll tell you what it does look like right now. It looks like a kind of odd parabola. Okay, so keep that in mind. If you can make determinations like this, so for example, if this was a parabola, then we'd expect this to look like a cubic. Because when you go from first derivative to the function, basically you take the antiderivative, think about integration, okay, the degree goes up. When I go from the function to the derivative, the degree goes down. Okay. Now, in this problem, they give us a starting point. I could graph that right away if I wanted to, but I'm going to do all the work first, and then I'm going to graph it. Okay. So, a couple things to think about. When I create my number line for the first derivative, what is the critical value? What is the critical value that I can get from here? Where does the sign change for the first derivative? Why? Go ahead, say it again, please. Right, so up here the slopes are all positive. Up here the y's are all negative, which means the slopes are positive, slopes are negative. So when I create my number line, and I'm just calling these endpoints 3.5, 0 is the place that I need to look. Now, we just talked about it, okay? We just talked about where the slopes are positive, where the y's are positive. The y's are positive over here, so I'm going to put a plus here, and they're negative over here, all right? Now, here's the information that's telling me. In my function itself, from 0 to 3.5, the function is increasing. That doesn't mean it's positive. It's just, it's going to have positive slope. And from 0 to 3.5, it's going to be decreasing, meaning the slopes will be negative. Okay? That's the information that I get from here. Now, the second derivative, that's a whole nother question. What values do I need to pay attention to for the second derivative? The max and mins, which are where the slopes are 0. okay? I just put those in there. I don't know why I put those in there. They don't need to be there. Okay, so at -2 and 2, I have horizontal tangents. So those become the critical values for this. And what that's going to do is tell me the concavity. Okay. And so now what I'm looking at is, all right, if over here, if I take the slope of the first derivative, that is actually telling me the second derivative. So from -2 to 3.5, so right here, what kind of slope do I have? Positive. From -2 to 2, what kind of slope do I have? And then from 2 to 3.5. Okay, what I've established here, here's what I've established. And to be honest, I'm going to take that out.
You made that number look so confusing.
How about now? Is that better? Yeah, let's get there. It didn't need to be there. Now, so here's what this means, okay? From -3.5 to 0, we have an increasing function. Okay, the slope will be positive. But it's concave up for part of that, and then concave down for part of that. I am going to put the 0 back in there for a minute. I think that's important to have at least the 0 in there. So here's what this is saying. In between -2 and 2, it's always going to be concave down. But it's not always going to be increasing. It's only increasing for part of it, and then it's decreasing for part of it, even though they're both concave down. Okay? So we've got to kind of keep that in mind. And then lastly, it's concave up from 2 and is increasing for that whole point. All right, now let's try to graph. And the easiest place to start is the starting point, 0, 1. Okay. When you have a starting point, there's not going to be the differences that we were talking about before with respect to vertical shifts. They gave us a starting point, so it's going to have to go through that point. Okay. Now, we're going to be decreasing this way, so it's going to even have some downward motion like this. We're going to be increasing toward that point this way. Okay? That's what this tells us. That's what this tells us. Increasing is going to go up to this point and just go down from this point. The trick is dealing with this concavity where it's both concave up and concave down until we get to 0. So at this point, -2, where x is -2, I have a point of inflection. Okay, so somewhere in here, I have a point of inflection. Now, did I take the slopes for any of them? I didn't. Okay, but you could. You could take the slope for the, no, I guess you wouldn't take the slope, because that's going the wrong way. All right, so how can you have something that's increasing and concave up? What does an increasing function in concave up look like?
A J.
I'm sorry?
A J.
A J. Is that a J? Increasing and concave up?
Yeah.
Agreed? Yeah, it kind of looks like that. What would be increasing and concave down? Is that just flipped? Can I just, if I take this, let's see if I can do it. Nope. First I'm going to duplicate it. How would I flip this thing? Concave down and increasing? What do you think? So both of these are increasing. This one's concave up. This one's concave down. Agree? Ish. Right? It's obviously not perfect. I totally just freehanded it right there. Okay? So, knowing that, if I'm going to start here at negative 3.5, I'm going to have to start down here because it has to be increasing. So it's essentially what I need to do is connect these, and that this inflection point would be here. So here's what I came up with. And one thing I want you to know, when you go to do this on your own, give yourself some grace. Try, do it again, do it a few times until you feel good about it. Don't half-effort it. Try to make it look as good as you can. I will tell you that when I made this presentation, I probably did it 3 or 4 or 5 times, okay? Because I wanted to make sure it looked good. So here's what I came up with. So that J thing, okay? So here's my concave up and increasing, concave down, increasing. Now, I missed the point, right? I missed it. So it's not perfect. It's never going to be perfect. But notice here that I started at negative 3.5, and I didn't put an endpoint, but there's an endpoint, right? There's no arrow there.
Why does this start at negative 2?
Why does what start at negative
Why
2?
is the y at negative 2 for negative 2.5?
Yeah, so do you not use values?
No, you don't even have a function to use to find values of.
So just like,
So you just pick a random.
So the only thing that I know is that there's an inflection point where x equals negative 2. That's the only thing I know in terms of where the concavity changes. That's the only thing I have to work with, okay?
You can make it like this too.
I can't see what, hold it up, will you?
So if I made my graph like that, it would be the same. Because the inflection's at 2, concave up and down. So
We could do, and we could compare, right? Like, if I look at this, at negative 3, the slope at negative 3 is almost 1, right? So at negative 3, my slope is, notice here, it's not quite a 45-degree line, the y equals x line, but it has this positive slope right there, okay? Not quite 1. We could look here and go, all right, at negative 2.9, it is 1. So at negative 2.9, right in here now, my slope is 1. So you could look for those kinds of things as well, okay? Same thing here, where x is negative 1, the slope is 1. So at negative 1, I have slope of about 1. So you have to kind of pay attention to that a little bit. And that's where you're going to want to kind of go through and check. Now, the thing that's nice about this other side is it's just the same thing, except instead of going from concave up to concave down, it goes from concave down to concave up. So this whole thing just flips over, and because it's decreasing, it'll look something like that, okay? And it'll have that kind of symmetry to it. Again, you can go back and check. So at 2, this looks like I have slope of like negative 2, right? So at 2, well, it's not quite negative 2. It's negative 1 1/3 or something, okay? But here I have like negative 1, right? Well, 1, negative 1. So at 1, I have negative 1 slope. So that's how you can kind of compare and use that to help you get that, okay? And again, there's not vertical shifts here because they gave us a starting point. All right. Other questions? We got one more. This is example 3. So same page 106. Now here we've got multiple graphs to graph. Okay? They've given us the derivative graph. We have to come up with the function, and we're going to graph the second derivative. So the understanding what we're looking at is really important here. Okay? So what kind of degree does this part have, would you say? Linear. So when I go this way from the first derivative, so I want to take the antiderivative of this, this is going to be degree 2, this part. This looks like what? This part looks like what? Quadratic, looks like a parabola. So when I go this way, now I'm going to have a cubic. When I go this way, this part of it, instead of it being a quadratic, it's going to be linear. What's a linear? When I take the degree, when I go, if the degree of a linear is 1, what's the degree of its derivative? 0. So what kind of function has slope 0? What kind of line? Horizontal line. So what we know is that, and we can do all, we haven't done any work. All we've done is a little analysis. Understanding that going from the first derivative to the function, I increase the degree. Going from the first derivative to the second derivative, I decrease the degree. Okay? Go ahead and try this one. And where I want you to stop, for starters, I want you to just worry about the function for now. Okay? And then we'll get to the second derivative after. And then we'll do a little check-in after you've got this one done. So go ahead and start on that one. All right, so first thing we want to do is take care of this number line situation. Okay? We notice here that the first derivative is positive above 2 because all these values are positive, and negative below negative. Okay, so negative 2 is where I really have to check. And so I'm positive here because these are all positive. I'm negative here. And what that tells me about the graph is that it's going to be decreasing left of negative 2 and increasing right of negative 2. Okay? As far as the second derivative goes, what's my only critical value here? Zero. Right here we have the little, I'd call that a cusp right there, sharp turn something. What will not exist here? The second derivative will not exist here because I have a sharp turn. So that's going to be important when we go to graph here. Okay, because the way I see this, I'm going to draw over it. I see it sharp, and then I see a, let me grab this kind of curve. Right, that's the way I view this, is that there's a really sharp turn right here. Okay, and that is here, which means it is not differentiable at that point. So when I go to do the second derivative, we're going to have to take that into account. But we're not going to worry about that right yet. Okay? So I would say our critical point is 0, x equals 0. Okay? But the slope of this part is positive or negative. Slope of this part is positive or negative. So now I can put the 0 up there. It's just positive everywhere. Which tells me the graph is always concave up, and there are no points of inflection. Okay? Now, let's get to this part that we were just kind of discussing. Actually, before we do that, I'm going to do my old piecewise function thing that some of you might remember. Okay? So over here, in this green area, the function needs to be increasing. Okay, over here, the function needs to be decreasing. Okay, so however you want to separate those sections of your graph is up to you. Okay, that's how I'm going to do it. Now, the other thing that we have here, and I asked about this, is there a relative min or a max? Is this telling me I have a minimum or a maximum? Min. What's another way that I can tell for sure?
The second derivative.
Second derivative test, okay, is always positive. So I'm definitely going to have a minimum at x equals negative 2. Okay. Concave, we discussed already, it's always concave up. Okay. Now, I'm just writing these things, and I'm not requiring that you have to write them down, but I think it's important when you're going through this to kind of get an idea. Now, some other things that we've talked about. This is linear, degree 1. So over here, it's going to be degree 2. Over here, it's going to be degree 0. We decided that this is probably degree 2, a parabola. Not necessarily, could be degree 4. But for all intents and purposes, if we think about it as degree 2, it's going to be fine. Okay. Now, so here got on this side. Okay, so from this portion, I have a minimum. Okay. I know that at x equals negative 1, I have slope of 1. So here I should have a slope of about 1. Here I have at -3, I have a slope of about -1. Okay, again, it's an estimate, not perfect. And notice here, these have arrowheads on them, so these should have arrowheads on them. Okay, so that takes care of my parabola part. If I go this way to here, I should have something cubic-ish. Now, part of our cubic, right, parts of cubics look like parabolas, thank you. One of the things that I think is important, though, is if I look at the slope at 1 is 3. So this one's going to be steeper. The slope at 0 is 2. So as I go to graph this part of a cubic that looks kind of like it's just going to be steeper than this one. Okay, and so there's a little bit of a change, but it juts up pretty quick. Okay, so the slope at 3 should be 4. So I've got slope at 1 is 3. So it's steeper, right? If I put a tangent line here, you'd see that it's definitely steeper than 1. And so that's where that one kind of looks like, okay? And so you can use some of that information to help guide what your slope should be. At x equals 1, the slope equals 3, so I have to have a steeper tangent line here where x equals 1, okay? This is where using colors I think is helpful because then it doesn't look like it's just a continuous parabola, that it looks a little bit different. All right, now let's go over here and work on our second derivative. We talked about this already. There can't be a point where x equals 0. Can't be a point there. We've got a sharp turn. It's not differentiable. So when I differentiate this, I'm not going to have a point, a value on the graph at x equals 0. Okay. Now, if that happens, okay, if the slope of this line we agree is 1, yes? Okay, so it's just going to be a horizontal line, and I just put an open circle at where x equals 0. The slope of this line everywhere is 1. Now the next part is where it gets tricky. Okay, the slope is 1-ish, then it's 2-ish, then it's 3, 4, and it starts climbing really quickly. So what is the slope really right here when x is 0? 0, right? We have a horizontal tangent. It just is not differentiable there, okay? So instead of starting right here at this point, what would make more sense is to start where it basically is 0, okay? And then then it's going to go up by 2, 3, 4. It's going to have some steep to it, okay? I made it go up as a slope of 2. Okay, it's steeper than just 1. Okay, so in other words, at 1, this is 2. So we're saying at 1, this, because if you look at this, right, the slope of this tangent line, if there was 1 there, it's definitely not 1. I went with 2. Could you have gone with 3? Sure.
Isn't the slope at 1, though?
The slope at 1, so right here. So we're saying, what is the slope of the tangent line right here? Because this is a slope, this is a graph of the slopes of this. So when x is 1, what we're saying is, what is the slope of this tangent line right here? I'll draw something in, okay? So in other words, right here. Slope of that line. You have to approximate, right? It's definitely not 1, though, right? I called it 2.
You know it means 0 or 4, right?
And then this could also be nonlinear, because if this was degree 4, then this could be cubic. Okay? Whoa.